episode of the MFG Radio Network's Lunch and Learn as we highlight some of the latest advances in manufacturing and design, gain insights about the newest products and technologies to move your manufacturing ahead of the competition. I'm Jake Kaufman, an associate editor for the manufacturing group here at GIE Media. We'll get right to the presentations today as we are joined by Blaser Swisslube. For more than 8 decades, Blaser Swisslube has been reputed for dependable first-class products that are human compatible and environmentally considerate. Their company stands firmly on the foundation of family values and Swiss competence. Today's presenter is Tom Capadona. He is Blaser Swisslube's product and process specialist for shops with grinding and EDM applications. He has over 35 years of experience in precision grinding with a focus on new product development and optimization. Today's presentation is called Choose the Right Fluid for Faster Feed Rates. So Tom, the floor is yours.
Thanks, Jake, and good afternoon, everyone. As Jake pointed out, I am the business development manager for grinding and EDM with Blaser Swisslube. I've been with Blaser since 2018, and I do have quite a few years of experience in grinding and related fields. So first, a little bit about Blaser. Blaser Swisslube is represented in 60 countries with physical offices, so pretty much any place in the world that metalworking is done, Blaser has a location to service that. For us here in the United States, this is our US headquarters. It's in Goshen, New York. We have both offices and a manufacturing facility. And lastly, a lab where we can test all of our products should anything go awry, or for that matter, to monitor the life cycle of our products when it comes to neat oils especially. The industry segments that we focus on are listed here. And for each of those, we have a specialty fluid, which is the best possible solution for these different segments. And the idea is to get the best possible solution for you in your applications. So we're going to talk about coolants, specifically neat oils, but just a food for thought when we get started here is that the coolant supply is really not relevant what coolant you use if the coolant does not reach the point of grinding. That being said, most of our customers spend millions, thousands, or hundreds of dollars on machines, and equally thousands of dollars for grinding wheels, especially when it comes to super abrasive, but they don't really pay much attention to how the coolant is actually making its way to the grind zone. I have a segment at the very end of the presentation which will talk about coolant delivery. But in the meantime, let's talk about the different types of coolants and neat oils. So you might ask the question, what is the difference between grinding with a neat oil or grinding with a water miscible fluid? And in a nutshell, the difference is water miscible does a great job of removing the heat once it's generated from the workpiece. However, oil, because it's got a lot more lubricity than water does a much better job of keeping the part cool to begin with. So as I mentioned, the primary tasks of the coolants and neat oils are to cool the part or actually remove the heat should it build up heat, but also to rinse the grinding wheel and keep it open and free cutting, as well as to bring lubrication to the grind zone as well. There's some additional tasks that the coolant is also responsible for as far as machine protection with corrosion and seals and hoses, as well as for the operator for good environmental health and safety, as well as easy handling of the coolant and to keep it stable. So during the grinding process, as you can imagine, you have hundreds or thousands of little points that are making contact with the part, and those build up heat. So the large majority of the power goes towards generating that heat, while only 3 or about 8% of the power is going towards forming the chip. So as you might imagine, with where the power goes with the different types of coolants. This slide shows a solution which basically contains no oil in it. And the next one is a light emulsion, which contains a small amount of oil, and then a stronger emulsion, which contains even more oil. And then, of course, a neat oil, by definition, contains no water at all. It's not mixed, it's used straight out of the drum. And what this represents is how much power does it take to push that grinding wheel through the grind zone and produce those little chips, albeit microchips. So as you can see from the solution, is the highest power draw down to the neat oil, which is the lowest power draw. These, however, can be modified. This is just a base solution, but they can be modified with additives to a certain degree to add lubricity and lower that power draw. Conversely, the more power it takes to push the grinding wheel through the grind zone, as you might imagine, the more wheel wear you're going to experience and wheel wear. So the best wheel wear characteristics would typically come from neat oil, whereas when you get with less and less oil, that wheel wear is going to increase. So now I want to talk specifically about neat oils. And historically, we've used crude oil as a source for the base oil. Obviously, you're not going to put that oil in that oil worker's hands into your machine. It has to be refined, that crude that we're talking about. Now, it comes out of the ground, so it has a fair amount of impurities in it that we want to focus on. So the first way of doing things is a mineral oil, where it's just refined and then gotten into the state where you can use it for a base oil. It's the least expensive way to manufacture oil. However, it doesn't do much for removing any impurities, and for that matter, having a very homogeneous chain length of molecules, which is responsible for the viscosities. The next one is a hydrocracked oil, where under pressure, those molecules are broken apart and then reassembled after it goes into the gaseous state, reassembled as homogeneously as they can be to create the viscosities that you're looking for. And it's a lot more pure and a lot more organized than the mineral oil version that we talked about to begin with. And then lastly, there's a PAO, which is a full synthetic oil. It's highly refined. It is very pure. And it's done in the same form. It's taken from crude into the gaseous state and then reassembled to get the base oil. It is machine and operator friendly. And I've got a chart here at the end that'll show you the comparisons between all of those. So the next step is we decided to, not we as in Blaser, but we as an industry decided to look at natural gas as a new source of base oil. So instead of crude, which comes out of the ground, we start with natural gas, which by nature, even though it comes out of the ground, doesn't have the impurities that you would get out of crude oil. So that gas is through a synthesis process, is turned into a liquid, and then it runs through a distillation process to get the exact viscosity that you're looking for. And again, without all those heavy refinement costs, is very similar to a PAO, and it's very homogeneous, as I mentioned, machine friendly, operator friendly, but most importantly, it's also more economical to manufacture. And it's an extremely clear product. This is one of our new test products, which is a gas to liquid oil, but you can see that it's pretty much water clear. And this particular one does not have, it has a very friendly aroma to it compared to some others that I have been exposed to in the past. The comparison of properties. So if you look at the attributes being flash point, evaporation behavior, aging, foam, and air release, the PAO and the gas to liquid are pretty much on par, where the further to the left you go, those attributes are not quite as strong. So when we talk about foam and air release, I'm going to show you a couple of videos here. This one on the left is not a gas to liquid oil, but as you can see, the milky foamy color on the window is the entrained air in the oil. And this next one, you can see the sheen on the window. Again, that's a gas to liquid, and it's nice and clear. And this one here, you can't even tell that you're looking through the oil until I pull back on this camera, and you can see it pooling up on the glass. And it's just that clear, and no entrained air and no foam. It's just, it's actually pretty amazing. The other thing with the flash point being critical is if you've got a lot of mist going on, it's quite possible that if someone has an accident, that mist can catch on fire. And nobody likes the machine fire. It's not good for the machine. It's not safe for the operator, and least of which you don't want to damage your shop. So flash point is very critical to that. And we do recommend fire suppression equipment in a machine just in case a fire were to occur. It can be put out rapidly. So burn marks, and I want to circle back to the base oils. I liken base oils for metalworking fluids to something that's dear to my heart. I love to cook. So if you look at a spaghetti sauce and you look at the tomatoes that you use to put into that sauce, you don't pick the finest tomatoes and get a good base for your sauce, and then you put the spices in, it's still not going to taste as good as possible if you've gotten the best ingredients. And same is true when it comes to metalworking fluids. You want the best possible base oil, and then to that you're going to add in your additives, and those additives will help with the base oil for the formulation. However, you don't want to start with a subpar base oil, and that's why we use the gas to liquid predominantly for grinding. So what we're trying to do here is, with that formulation, we want a gear that looks like the one on the left, where there's no burn marks, and that we can perhaps increase our feed rates because we've got the lubricity there for that. The one on the left shows some burn marks in there, and it's probably because there's not enough lubricity, or the coolant isn't being delivered properly to the grind zone. The other point is that entrained air. You might ask, well, what problem does that cause? And the more entrained air that you have in the coolant, or the oil, if you think about it, the less coolant or neat oil is making its way to the grind zone and protecting you against this kind of burning. So it all goes into play when it comes to producing a quality part that's free of burn marks. We talked about additives. These are some of the additives that can be used depending on what the goal is of the particular coolant that's involved. And they all trigger at different temperature rating, different temperatures, as you can see from the line on the bottom. Now we're going to take a quick trip to Switzerland, and this is our laboratory in Switzerland, where we can test all the products. As I mentioned, we can test for problems should they arise, but more importantly with a neat oil, because typically we don't have problems through the life of the oil, which can be as long as 8 or 10 years, is when to plan a changeover, depending on what the trends we see in the samples that were tested. We also have a tech center in Switzerland where we can and do test all of our water miscible coolants and neat oils. We can do that right in this machine and make sure that we've got the quality that we're looking for before we go out and field test and do run field tests before we release it as an actual product. We have 2 different tech centers, actually. This is the grinding tech center, but there's also a machining tech center, which is a totally different location. So to the heart of what we were talking about in our increasing your productivity by getting more parts out of the process. So by reducing the load on the grinding wheel, and we'll talk about that in the next couple of slides as well, the different forces, But by reducing the force on the that it takes to push the grinding wheel through the workpiece, we can increase our feed rates because that power draw is down and we're not causing any burning, and therefore we can get more parts per whatever hour, day, minute, whatever you want to measure it by. We're also interested in the number of work pieces between dressing, or in the case of tool grinding, conditioning the wheel. That's a time saver as well. So here we want to talk about the difference in the forces that are applied during grinding. So the tangential force is the amount of force it takes to push the grinding wheel through the work zone, as we've got all those hundreds or thousands of points making their own chip at the grind zone. That's basically the power draw on the grinding wheel, on the grinding head, the grinding wheel. There's another force, because the more lubricity and the lower the tangential force, you're going to end up applying pressure into the part, which is called the normal force. So again, the higher lubricity, the lower the tangential force, but the higher the normal force. And as I say in grinding, unfortunately, nothing is for free when it comes to grinding. If you get something, you're probably going to have to give something up. And we just have to be careful with the tangential force and the normal force, because the tangential force causes lower, if you lower it, it reduces the power consumption, as I mentioned, and less burning. But the consequence is that you're going to push harder, and it could cause vibrations or chatter, or could even push the part out of the centers in the case of cylindrical grinding. So these are all things we have to take care not to exceed and be aware of, because the last thing we want is someone to get hurt or machines to get broken. So the delivery of the coolant, this is the section that I talked about with my first or second slide. If the coolant delivery is not ideal, then you are going to end up with entrained air and not the best possible amount of coolant getting delivered precisely to the grind zone. So if you notice in this slide, the lock line, I'm not a huge fan of lock line, because the inside of that isn't smooth, and it can build up a lot of turbulence and induce entrained air. And again, the more air you have instead of coolant or neat oil, the less protection you're getting to the workpiece as it's being ground. So I kind of liken this as the fire hose approach. It just sprays coolant everywhere, but it's not really uniform and laminate and in the place where you want it to be. So the next best step would be to use a smooth tube. I've done this myself, but I can tell you from experience that'll eliminate the turbulence, but it's very difficult to get out at the end a very uniform opening that doesn't still disperse the coolant in a way that you don't really want. And again, we don't need that entrained air in there. So the ideal solution is a manufactured nozzle to fit on the end of that tube. And as you can see here, that flow is now more laminate and more directed. It's not spraying on the sides of the grinding wheel as it was in the other picture. Additionally, you can control the velocity of the speed of the coolant as it gets to the grinding wheel and match that speed of the grinding wheel. And you might ask the question, well, why do you need to do that? When the reason is because as the grinding wheel spins, it creates an air envelope, an air jacket, if you will, and the coolant can't penetrate that. If it's going slower, or for that matter, even faster, it'll deflect, and you can actually see that if you look at it closely in a grinding machine. So what you really want is to match the velocity of the grinding wheel or the coolant to the grinding wheel, and hit the grinding wheel just prior to the grinding wheel entering the part in the work zone. That would be the ideal situation. And as I mentioned, this is a machined part. They're precision parts. You can see it here where it's restricted down in a very uniform way, very smooth walled. And the end result, as you can see in the picture, is a laminate stream that goes directly into the grind zone and not dispersed throughout. So in summary, the coolant has primary tasks and additional tasks that are involved that it's responsible for. The newest technology today is natural gas, which is in the base oil without a lot of refinement. It's very pure and it has all the positive attributes that you might have out of a full synthetic, but without all of the manufacturing costs due to refining. And then you have better lubrication to lower that tangential force, which is critical in being able to improve your process. Then you can increase your feed rates without the fear of burning, but you do need to keep an eye on the normal forces that you're creating, because if you go faster but you don't have a quality part, that's not good either. And then of course the coolant delivery has to be taken care of. You can lose all of the things we've talked about with the coolant quality or neat oil quality if you're not putting it in the right place and at the right speed for your process to achieve the best possible results. This is a customer in Switzerland. I've actually visited this facility twice, and they're running our Blaser Grind GTM10, which is a 10 viscosity. And as you can see in the caption, the operator is very pleased with the way our oil is performing for them, and for that matter, the soft factors that he has to deal with on a daily basis. And with that, I will take any questions that might have come up.
Awesome. Well, thank you so much there, Tom. Looks like we do have a few in the audience, as Edward would like to know, water-based coolant removes heat better, but oil doesn't let it build up to begin with. Is that true?
Actually, no. What happens is the oil does a much better job of providing lubrication. So as you might envision, if you had a file, for example, and you're running that file over steel, it's going to make the steel hot. However, if you add some oil to it, that will help with the friction and reduce the heat. If you just put water on it, it will reduce the heat, but not as well, but it'll help keep the part cooler. So the part will get warmer to begin with water, but that friction will be much less when it comes to oil. Did that answer the question?
I believe so. We also, Edward would like to know, is GTL now common with high quality oils, or is PAO still prominent?
Both are out there on the market, but again, the quality is fairly much on par. However, the refinement costs, as I mentioned, are definitely lower when it comes to a gas to liquid, and therefore we feel that it's a better option. However, the guys with the PAOs would probably argue that, but there also is, because of the way the molecules are assembled in the PAO and refined, it's also difficult to get the additives to stick to that oil. They can come out a lot easier than they can, just because it's a lot more homogeneous when it comes to a gas to liquid.
Awesome. Thank you, Tom. So we also would like to know, how do you see coolant selection improving productivity?
A lot of different ways. The key things for us when it comes to a neat oil anyway is the filter system manufacturer. A lot of them have different requirements, and conversely, some of the machine tool builders also have requirements on viscosities. But the type of material being ground is critical to us, because we have some that are specific for just steel, and the additive package is designed around that. We also have some that are designed around carbide grinding, and carbide contains cobalt, and you need to make provisions for that because it is a health and safety issue when it comes to the operator.
Awesome. Thank you, Tom. So then how would you measure that, or could you give an example of that?
Well, the cobalt we can measure through our lab and taking those values. As far
Mhm.
as, yeah, well, the way you would measure that would be to run a test, if you will. And we've done that in our laboratory. For example, our GTS, and the S stands for steel, as opposed to GTM, which is multi. So
Mhm.
that particular example I gave earlier of the GTM 10, that's being used on carbide, and that can handle the cobalt. However, we have a GTS product which is specifically designed for steel. So in the event of only steel, you're going to get better performance out of the GTS 10 versus the GTM 10 on steel.
Okay, awesome. Thank you, Tom. And looks like we have one final question from David. He says that they have an air quality problem in their shop. So they use air to blow out contaminants after removing parts from their mills. Is there a coolant that would be ideal for that kind of application?
Again, the gas to liquid, and I don't know if he's referring to water miscible or if he's referring to a neat oil, but certainly that's what we strive for, is lower mist emissions during the grinding process. And that all has to do with the droplets that are formed in grinding. I mean, it's difficult when you've got things moving at high speed, but certainly we strive to minimize that, because I know exactly what he's talking about. When you open the door and the cloud comes out and gets you, it's less than ideal, and nobody goes home stinking like whatever you're grinding in.
Yeah. Awesome. Well, thank you, Tom. That just about wraps up the presentation from Blaser Swisslube. So thank you so much for all of the insight today, Tom.
Thank you much. Pleasure's mine. Anybody has any further questions, feel free to reach out to me.
You can find more Lunch and Learns plus the MFG Radio Network's other podcasts on Apple Music, Spotify, Google Podcasts, or on our websites at todaysmedicaldevelopments.com, aerospace manufacturing and design.com, and evdesignandmanufacturing.com.